All right, I think we can start with the introduction. And thanks to everyone for joining us today. Antonio Cabas Vidani is the product manager of Fluxim, specialized in thin film photovoltaics. He earned his PhD from the ETH in Zurich, and his research at that time focused on Perovskite thin film photovoltaics. Antonio joined Fluxim in 2021 as an application scientist and is now the manager of our solar cell stability platform called LithoSlide. The title of Antonio's talk is Stability of Perovskite Solar Cells, Literature Overview, Best Practices and Tools Required for the Analysis. Thanks a lot, Antonio, for preparing this. The floor is yours.
Thank you. Thank you, Daniele. Let's start. Let me share the screen and open the presentation. You should be seeing it and hear me loud and clear, correct? I don't see you. I take it as a yes.
Yes, this is correct.
Okay. Okay, perfect. Yeah, indeed. Let's start with this presentation, and it's a collection of observations, our studies, tips and tricks we want to share regarding perovskite stability. So let's start with a more generic overview. We can see that perovskite, its stability is studied as a very big issue. It lasted no more than maybe 1 hour under continuous simulation, and now we are going towards 1,000 hours, 1,000 hours goal. Let me turn on the pointer first. The fact that perovskite lasts for 1,000 hours, it's intended as after 1,000 hours, it reaches 80% of the initial performance. This is T80 stability. Now we're on a good track. Sorry, it's not. Yeah, we're on a good track. We clearly see the improvement, but we need to push further. We need to push further because the goal is 20-25 years in order to be a good match for silicon solar cells, for instance. And overall stability is a rather complex topic, so we need to move beyond just MPP tracking under continuous illumination, right? So let's take first a step backward in order to move forward. What is effectively stability? Stability is the combination of multiple stressors. This entails intrinsic stressors and extrinsic stressors. The latter one is essentially how your device behaves when it's subjected to the environment, so oxygen and humidity essentially. And you see that each stressor has a wide variety, a wide range of intensities. We can go with light, going from dark up to sunlight. So this would be outdoor conditions. We have the bias goes from reverse to MPP and all the steps in between. And then the extrinsic, so the humidity essentially can go from inert, so no humidity, up to 85% if you want to create especially stressing environment. Now, the point is how to match it, right? How to connect all these stressors in order to get the stressing environment that you want. Well, for that, we have protocols, right? They provide a framework for reliable stressing comparisons. And the two main ones are IEC and ISOs protocols. Now, they are similar in the sense that they both focus on getting reproducible and comparable testing results. And also they both aim at combining stressing conditions with characterization. And with characterization, we typically mean at least a JV measurements in order to get the efficiency, because efficiency not always matches with the MPP at operational conditions. But they are different. They are different in the sense that IEC is based on industrial facilities, so what is available in the industry, in the research laboratory within the industry, whereas ISOs is informed by academic research. So similar, but with different approach. Let's see how different actually they are. So in terms of IEC standards, you already see that from the title, they are not enough for perovskite. They address the stress that you can find in the outdoor environment, and this is how their protocols are structured. So they try to replicate similar specific set of conditions that you find in the outdoor, but one thing that they miss is a gradual increase in measurement complexity. So this means that if you take a protocol, you need a very specific set of facilities, set of equipment and tools to recreate the protocol instead of starting from a simpler level. And then they're not adapted to perovskite. And this means, for instance, that if we take the T80 as standardized figure of merit to assess the stability of perovskite, then we see that this figure of merit is not compatible, or it's difficult to make it compatible, let's say, with special decay behaviors typical of perovskite, like the burning effect that you see here on the left, where the performance first increases and then decreases, or the reversible decay, where if you cycle, so you turn on and off the light, then you see that actually the loss in performance is recovered after a time in the darkness. And this is why we have ISOs protocols, and they are informed by the academic research indeed. And here the idea is to effectively just understand the stability, and they're grouped based on the applied stress. You can see here from the table, this means that whether you apply a light, whether you apply a bias or a temperature, then you are dealing with a different kind of protocol. And then each protocol varies in complexity, so has increasing complexity. You can see here it starts from D1. This essentially means you put your solar cell in the darkness, in the shadow, the smoke arc in the darkness, and you just keep it at room temperature. So this is very easy, attainable for any laboratory. But then if you want to go farther, you can increase the temperature and you go to D2. And from there you can again vary and maybe get rid of the atmosphere. So you get D2I, you see here on the top. Or you increase the humidity, for instance, for additional stress. On top of that, it also provides protocols that are specific to perovskite. And they're specific in the sense that they aim at conditioning or studying the perovskite for its ions contribution to the stability, or to study the reversible degradation that we just mentioned, as well as intrinsic degradation that I just indicated with a protocol. And on top of that, we also that it evolves with the research community. I said that T80 is not enough, and in fact, I have a bunch of other figures of merit. You have T80 stabilized. This is indeed for the stability effect, or the efficiency after 1,000 hours, so on and so forth. Now we have the framework, which is ISOs protocols. But then what does it take to perform this kind of measurement? You need the right tool. And not only you need the right tool to replicate these protocols, but you also want reliable comparisons. You want your results to be statistically valid. This is why the tool that you are going to consider for your stressing experiments should manage to do parallel stressing. So this means all pixels are stressed at once, and also parallel JV. In this way, you can both measure, have stressing conditions and characterization. As I mentioned, this is a key factor in the protocol. Stressing on its own is not sufficient. In addition to that, you also want the possibility to apply any sort of bias, which means positive, negative bias. Same goes for the current. You want the sun simulator to be software controlled so that you can automate and coordinate the measurement, the bias, so to speak, with the illumination. You want to cycle your type of measurements, and you also want to control the environment if you want to get, for instance, controlled humidity or intrinsic atmosphere. And what we have typically in a laboratory is an SMU, like a Keithley, for instance. Here you definitely don't satisfy many of the requirements. You have a very good high quality JV measurements, but only for one sample at a time. Then common choice is also NPP tracker. This is just a representative board we have on the top, which is good for parallel stressing, but it focuses, as it says, on NPP tracking. It has sequential JV, not parallel JV, and depending on the implementation, you might or might not have controlled sun simulator and environment as well. And then we have Litos Light. This comes from Fluxim, and indeed we focused on all these requirements in order to push further with the stability research. Now let me show you, for instance, some examples of how this instrument can be used, and it's currently used in the research. Here we have a study on passivation. And the idea is to compare the impact of bulk and surface passivation on stability. In this very specific case, I will not specify what kind of passivant is used. It's just they compared the chain length of cations and tested the stability in order to see their impact on stability itself. So what they observed was that if you have a long chain cation, then you're passivating the surface. If you have a short chain cation, then you passivate the bulk, and this helps in slowing degradation. And for this, they used indeed litho's light, and they performed MPP tracking measurement, but in an into-reach atmosphere in order to, so this is intrinsic atmosphere, in order to get rid of any possible influence from the environment. And you see also already the importance of parallel testing, because then you have direct comparison of the stability measurement of devices with a different passivation. Now, not only the absorber, the perovskite absorber needs to be tackled, but also its crystal phase stability, the thermal stability of its crystal phase, to be more specific. Now, this is a study that comes from Georgia Tech, from Lafayette et al. I hope I didn't butcher the name. And here they compared, here it's a bit different because they didn't study directly the stability, but they did parallel JV testing in order to see the impact on PC. And as I mentioned, this is a key part of understanding stability. And what they compared was absorber with and without bromine. In this case, the importance of bromine is that, or the use of bromine is that it increases the room temperature stability of the crystal phase, but at the same time, it accelerates the phase degradation. Now, the mechanism is a bit complex. To just say it enhances the formation of vacancies, and this eventually lead to also lower stability. To understand that, what they did was indeed parallel JV, and they needed all the devices to be at a very specific temperature and in a comparable environment. In this way, they get indeed a statistical distribution of the performance from their devices. Again, was performed with litho's light, which allows to load multiple and measure multiple samples at once. Now, I mentioned the thermal stability of the crystal phase, but from Grottement et al. This comes from MIT. We have that the device as a whole should be stable, right? And what he noticed was that whole transporting layer, like spiral meltad, which is rather common for high efficiency perovskite devices, it has low stability, meaning temperature, meaning that it's stable up to 85 degrees. Now, this is a bit too low for a typical use case of solar cells. So you rather want something that withstands higher temperature. This is why he developed an additive-free spiral meltad hot transporting layer that reaches up to 115 degrees. In this case, again, he didn't want any contribution from the environment in order to fully focus on the stability of the transporting layer, and he also needed to measure multiple samples in parallel. So this is why he went for a larger solar cell, a larger sun simulator, connected again to litho's light, and the performance was tested at 85 degrees. And you see here the efficiency, overall efficiency is rather low, but it was rather stable over more than actually up to almost 1,500 hours. So this is an indication that the hot transporting layer needs quite some attention. Now, we performed as well studies on degradation. We not just sell, of course, the product. We do science ourselves. And what we notice is that aging influences also mobile ions. Now, perovskite is known also for the very mobile ions, which affect the aging, but aging itself seems to be affecting the ions. Let me show you what we did. We first of all performed MPP tracking of a very specific perovskite absorber. This is a cesium-based FAPI, and the device is intended for bifacial applications. We performed it in low humidity, and we could reach up to 400 hours, T90 in this case, so it's 10% of the initial, up to 10% of the initial performance. And we combined that with rather advanced characterization. What we wanted to see was indeed if the ions signature of the, if there was any change in the density, mobility, anything related to mobile ions. So what we did, we performed open circuit voltage decay measurements where you shine a light on the sample, you turn it off, you keep the sample at open circuit voltage and see how this decays. Now with a rather complex, I would say, elaboration of the data, you find everything in the paper from Fisher et al. You can extract the ion density of your perovskite layer. And what we observed here, you see on the right, was that the H device, regardless of the light intensity, had always an ion density that was up to 2 orders of magnitude higher than the fresh device. This was rather interesting observation, but interestingly was confirmed also by Tisbrummel et al. Tisbrummel from Oxford PD. Now the exact reasons behind it is unclear, but is observed on multiple type of perovskites. And indeed, always Tisbrummel also quantified the effective impact of mobile ions on the PCE and on stability itself. Now, to do that, she performed JV scans in a wide range of scan rates, up to a scan rate of more than 1,000 volts per second. In this way, you reach a state where your ions are not moving. So this means that that is the effective PCE, effective performance of your device, assuming there are no mobile ions influencing your performance with a field screening effect. And she performed this kind of measurements also on degraded devices. So what she did was indeed H, a device, a perovskite device. In this very specific case, she considered multiple types of perovskite absorbers. And she noticed that after the degradation, after about 1,600 hours in this case, indeed the measured PCE as obtained from the NTP tracking was way lower than the starting point. But if you perform a JV with a fast scan, so ion freeze conditions, then the PCE effectively is recovered essentially, or it's actually not lost. So this really indicates the importance of mobile ions on performance measurement and on stability itself of the perovskite. So far, we talked always about operational stability. So this means positive voltages, but reverse bias is also absolutely crucial for commercialization of solar cells. Now, reverse bias is a special kind of testing. And this is why I mentioned you need a tool that allows you to measure potential and current in any of the 4 quadrants of the IV plot. Because with the reverse bias, you mimic a real case condition, which is partial shadowing. This can be leaves, can be birds, can be a stone, anything that lands on your solar cell. And the perovskite is known to be rather unstable, or I believe to shunt and destroy itself if you keep it at low at reverse bias conditions for long. But what was observed was that if you have a carbon-based electrode perovskite, then it can withstand a negative voltage up to -6 volts for 20 minutes. So this is a very specific kind of perovskite that would indeed be suitable for outdoor conditions, real outdoor conditions. But if you don't have, of course, a carbon-based electrode, as I said, it's a special kind of perovskite, then you're stuck with a single junction perovskite that is rather unstable to reverse bias, meaning that after a reverse bias of -2.5 volts, which is not large, considering the variation that you might have in the outdoor, you have the JV that eventually is not reproducible enough. Again, I would like to stress the importance of parallel JV. It's in this way that you can get a real comparison of device stability. But if you combine the perovskite together with silicon, now here we're talking of silicon perovskite monolithic tandem, then we see that silicon is actually getting most of the reverse bias, and so the overall device is almost as stable as the silicon instead of the perovskite. So this is also an alternative way for commercialization of perovskite, and it looks indeed rather promising in this direction. Now, we covered a lot, and I mentioned multiple times the importance of parallel testing, but I would like to leave you with one last observation that comes directly from our laboratories and from together with our customers, which is the sample layout. In case of parallel testing, it actually matters quite a bit. And it matters especially if you have a pre-structured TCO. This is often a choice for lab-scale devices, where laboratories get a pre-structured substrate with a TCO on top. And the TCO acts as an electrode for your pixels. You see here a schematic top view of a sample with a common electrode, so one electrode that connects to 2 pixels. And it also happens that this electrode is non-metallized. Now, why is this a problem? Well, if it is not metallized, then we have a higher resistance, and this leads to a deviation of the voltage you measure. So you don't effectively measure the VOC or the NPP of your pixel, or you don't measure the real VOC and NPP. And then if you have a common electrode instead, here you have actually an influence that is a bit more difficult to quantify, because it depends on the electrical status of the neighboring pixel, and it also depends on the total amount of pixels connected to that same common electrode. Let me show you a quick example. Here we have indeed these 2 pixels. They are under measurement, and one of these pixels is shunted. And on the right, you have simulated JV for these 2 for pixel 4, so the one that is not shunted, with increasing resistance of the common electrode. You see here the resistance grows from almost 0 up to 100 ohm, passing through values like 1 and 10, which are closer to reality. Now we can see that the higher the contact resistance, the higher the resistance of the common electrode, so to speak, the more the curve shifts to the right, the higher the overestimation of your NPP and the VOC. So I guess it's quite evident here the importance of avoiding a common electrode and possibly avoiding high contact resistance. And this is why indeed the solution is to have, yes, you can still have multiple pixels on the same substrate, but ideally the contacts should be individual for each pixel, and they should be metallized. So let me wrap up everything and leave you with some main observations. Perovskite stability is improving. We saw it, and we can appreciate it from the large amount of data you find in the Perovskite database. But if we want to push further, NPP tracking is not enough. We have to look at ISOs protocols, which provide a clear framework on how you can tackle and understand stability. And for that, you need, of course, appropriate equipment, which allows you for parallel testing so that you have reliable comparison, and control also of illumination conditions and environmental conditions, ideally, so that you can match as many ISOs protocols as possible. Last but not least, if you are dealing with lab-scale devices, please make sure that your layout is effectively ready for parallel testing, or that in any case is not contributing to the measurement as well. With this, I would like to thank you very much for your attention.
Thanks a lot, Antonio. This was a great overview. I really appreciated that. Let me ask you quickly one question. You said that the ISOs protocol are made for perovskite solar cells. Do they cover all the needs that we have on perovskite solar cell stability?
Yeah, it's a fair question. Well, as I mentioned, the ISOs protocols they evolve together with the research community. So at the moment, they cover many conditions and many stability cases, many stability or decay profiles, many behaviors of perovskite, so to speak. But of course, they are ready to evolve together with a perovskite. In this very moment, for instance, I can tell you it focuses mainly on operational stability, but from my perspective, it misses a bit the let's say guidelines for reverse stability. It's not. We saw that you can find in the literature that it's a rather complex topic by itself. So it really strongly depends how you what's the history of your device. And this should be taken into account, and also there are some guidelines on how to perform reversibility in order to have a framework.
Antonio, this is for you. They're asking you, what about masking after they heard that you're avoiding a common electrode because this technique doesn't work with the parallel measurement. So what about masking? Should it be larger, smaller? What's your take?
Yeah, that's a very fair question. I couldn't cover it. We analyzed that, and we will add the results to the website as well. So in short, as we all know, masking, first of all, is necessary to avoid JSC overestimation. But at the same time, masking can easily lead to VOC overestimation. Now, of course, that is good because it gives you better PCE, right? But then if you go to certify, then you don't see that overestimation anymore. So what we notice is that, yes, it's good masking, but even better if you can scribe around the pixel. In this way, you avoid any influence from the neighboring areas or from layers that are common to multiple pixels.
Yeah. All right, it's already 11 o'clock, so let's close it up. And I thank you a lot, Antonio. Great job. In 1 month, we are going to be here again, and soon you will learn about the new topic that we have in mind.
Yeah.
Thanks a lot to everyone.
Thank you.
And have a good day.
Yeah, thanks a lot for joining. Keep in touch. Bye-bye.
Bye-bye.
Bye-bye.